Okay, thank you very much, Steve, and thank you all for inviting me. I don't mind at all because I prepared this talk a couple of years ago, and this is about the third or fourth time I've given it, so it's paying me back now for all the preparation. So I always think that's a better investment than giving something once. I'm just going to share my screen with any luck. I don't know why. Here it is. This should work. Right, can you see my my title?
Yep, it's come up nicely.
Right. So my title really, Glass Unsung Wonder Material. I say unsung because I've been in universities all my life in various material science guises, started as a metallurgist, but glass is a very widely used material, but very understudied in a way. You can't, there's almost nowhere in the country you could go to study glass at university level. There used to be a department at Sheffield, but that closed and merged into material science. So it is a wonder material, but students don't learn much about it, which is why I first wrote this lecture for a bunch of students. And I delivered that face to face, and I took the various bits of glass I'm going to show you, I took along. So they actually got to handle things, which I'm afraid we can't do today. So here's my talk. I've tried to keep it to, oh, it's not. Yeah, there we go. I've tried to keep it to 45 minutes, so I'll censor myself at that sort of time. Here's a biblical quotation. Pointing up, of course, that glass has so many meanings. In the biblical sense, it meant mirror, not, of course, glass as a material. So that's what is implied in Corinthians, through some glass darkly, but now face to face. And the piece behind it is by a guy called Panizzi, and we bought it in Murano. My wife collects art glass, and almost every slide of this presentation has a piece of art glass on, and I've attributed its artist somewhere in the screen. So if you replay this, you can find out who the artists were. So there we go. It's by me with glass by my wife, Gwen. When I say by, she owns most of it. There are two pieces that she's made in here, which I've attributed to her, but mainly it's just stuff she's collected. And one bit is owned by me, which I shall point out on the next slide, because she bought it for me because I loved it. So that's a bit of background. This is the bit I own, and it's by a London glassmaker called Peter Layton, who's quite famous, and it's a homage to Hockney. The vertical lines are like the trees in Hockney's paintings of a few years ago. He went through a phase where he painted a lot of vertical trunks of trees, and this was the glassmaker's homage to Hockney. My rather pathetic attempt to justify showing you lots of glass. Bernard Shaw said, "You use a glass mirror to see your face. You use works of art to see your soul." So there's my admittedly pathetic justification for talking to you. Right, so types of glass. You'll have heard the word glass in lots and lots of contexts. So here's a piece, a bowl by James Charles. It's actually a very bad photo, but I thought the dottiness turned out quite nicely, so I'm using it. Here are some of the ways in which you might, or the contexts in which you might have thought of glass. So we use glass in architecture, art glass I've just talked about. We have blown glass, borosilicate glass, crystal glass, which I shall be talking a bit more about, fiberglass, float glass, laminated glass, lead glass, metallic glass. All of these I'm going to say a little bit about. Mirror glass, which I'm not going to talk much about, photochromic glass, plate glass, lump glass, toughened glass, volcanic glass, window glass. And it occurred to me I'd missed out eyeglass, and that was brought to my mind because our last U3A speaker here in Chester had a false eye, which he pointed out to me rather proudly, which wasn't actually made of glass, but we still call them glass eyes. And we've encountered glass in huge structures like Crystal Palace, in the glasses that I'm wearing and lots of you are wearing now, as marbles, as oops, I'm just trying to I like to get a few of you visible, because I can tell if at least 5 of you are going to sleep, and I know I've got to jazz it up a bit. And if I'm talking to absolutely nobody, I can't tell that. So none of the 4 of you in camera appear to be asleep at the moment. So I'll take that as encouragement. So bottles, optical fibre, faience. I put that in because I didn't know what it meant when I first encountered it. And you might think that faience came from Faenza in Italy. That would be a logical conclusion. It doesn't. It actually is a glassy glaze which the Egyptians started using. And here are 2 pieces of, if you like, pottery, but their glaze is glass. And that was done by the Egyptians some long time ago. And Faenza in Italy, after which faience is apparently named, has very little, if anything, to do with it. Well, that's just a side useless fact. Here are 3 pieces that currently decorate our bedroom, I think, which we picked up in various places around the world. But I'm using this as a background to introduce some of the questions I want to attempt to answer. So, why can we see through glass? It's not absolutely obvious. Glass is brittle, yet we know it's used in toughened circumstances. So how can it be toughened? A little bit of history. Who first used glass? It goes back a long way. Why is glass so resistant to attack, except, as I shall show you later, by hammers? Why is crystal glass an oxymoron? And I'll hope to explain that. What is the glass transition? I'm actually not going to talk about that. That's a bit too material sciencey, and unless anyone asks me, I'm going to skip that bit. So those are some of the questions I'll be addressing, but let's start with a definition of what I mean, and I think the world means, by glass. This piece by Sally Dunnock won 3rd prize in a biennial glass competition in Stourbridge, and so we bought it at an exhibition, and it was a prize winner. It's an example of slump glass, which I shall come to at the end. So, my definition. A glass is a material that has hardened and become rigid without crystallizing, making it amorphous. So, the essence of glasses is hard, amorphous, not crystallized. So more of that later, but it's a very important distinction. Let's go on. Let's go back to a bit of history. So who first used glass? That's a nice piece by Catherine Half, ostensibly a perfume bottle, but merely an excuse for those shapes, I think. So who first used glass? Here's a very, very brief history. Volcanic glass was used in the Stone Age, and it was called, and is called, obsidian, and I'll show you some pictures on the next slide. Glassmaking took off thousands of years BC in Mesopotamia or Egypt, at least 3,600 years BCE. So it's a very, very old technology, if you like. Cheap glass was really exploited by the Romans in the Roman Empire. So you'll be aware that lots of glass bottles have been dug up from Roman sites. Romans used and traded glass heavily. And I'll say a bit more about what glass they used in a minute. And then in art terms, it became a skilled trade, if you like, in Bohemia in the 13th century. My wife has been trying to trace her ancestors back, but she hasn't got as far as the 13th century because she believes that somewhere in her prehistory are glass artists because she's so interested in it. She hasn't got that far back yet. More famously, in today's context, a glassmaker started in Murano, just off Venice, one of those islands just off Venice, in the 14th century. And if you don't know much about glass, I do recommend a visit to Murano. You can see it being blown. It's quite fun. We brought a couple of pieces back from there, including the first one that I showed you. Then, skipping a few hundred years, float glass was famously a British invention by the Pilkingtons, and still, of course, made in St Helens. And that was in the 1950s, and I'll say a bit about how that's done at the end. And then a little bit more up to date, because it's a very timely topic, although it was invented quite a long time ago. Optical fibres, which we use now. I mean, a lot of this presentation is going down optical fibres as we speak. But actually, it was an invention from the STL lab in the south of England in the 1960s by a guy called Cow, who was a Japanese origin, I think, or Chinese or Japanese origin, I don't actually know. But it was invented in the UK, and we know that's spread the world. So that's as much history as I'm going to cover. So I've covered about 5,000 years in one slide. Let's just look at obsidian. That's a piece of obsidian, as I said, volcanic lava. So obsidian is naturally occurring, and it's a glass formed when a volcano cools rapidly, so rapidly enough that crystals can't grow. So it's an igneous rock, and interestingly, I'll come back to this point, so think about this. It's produced from lava rich in lighter elements such as silicon, oxygen, aluminium, sodium, and potassium. And the fact that that list is long is of some significance. So that's obsidian. Of course, if you are of a mystic persuasion, then you can go and buy a bit of obsidian in your local mystic shop, and they will tell you that it's a strongly protective stone, forming a shield against negativity. Often in the depths of my despair as being chairman of U3A, I think in Chester, I think I need to take out my piece of obsidian and use it as a shield against negativity, but it doesn't seem to work too well. It blocks psychic attack and absorbs negative energies from the environment, draws out mental stress and tension. Boy, could I use it, but I'm afraid it doesn't work. So that's obsidian. That's where we started. Let's now talk a little bit about the composition of glass. This is quite important, it seems to me. Two pieces here by Catherine Huff, one of our favourite artists, just a vase and another bottle. Composition. I'm going to put up the composition of, if you like, bog standard window and bottle glass. Soda lime silicate glasses would be typically, don't hold me to this, 70+% ish of silica, 16 or so weight percent of soda, and 10 weight percent or so of lime, calcium oxide. Now, why? Why those three materials? Well, the silica is the glass former, but it needs to be worked. It melts a bit below 2000, but it needs to be worked if you're going to move it, change its shape around, above 2000 centigrade, which is a very high temperature. Inconvenient to get, expensive to get. So adding the soda as a flux reduces the working temperature considerably. And I'll say a little bit more quantitatively about that in a minute. And then adding the lime, it's a stabilizer, and that prevents the whole thing dissolving in water. So those are the three principal constituents of ordinary glass, and of many glasses actually. Then there may be minor additions, which I'll talk about in a minute, to achieve particular effects, but that's the base. And then that's a nice bit of patterned blue glass from Ireland. Then you can add to the basic glass lots of other oxides. All those were oxides. That glass, when molten, dissolves lots of other oxides. So you've got a whole palette of stuff you can shove into glass and it will dissolve. So you can do that to tune its colour. And I've shown you many examples of colour. Interestingly, red was one of the hardest colours to get by glass artists. You can change its density, and I'll say a bit more about that in a minute. You can change its refractive index, very important when you want to use it for optical transmission. You can change its chemical resistance, and you can change its infrared absorption. And Pilkingtons are quite interested in that in terms of windows. So you can tune glasses in a quite wide variety of ways, is what I'm saying. And to do that, you can add a lot of oxides, of which perhaps the most common would be aluminium, boron, lead, barium, cadmium, chromium, and both types of iron oxide. Lead is becoming less popular because of its well-known toxicity, and I'll say a bit more about that a little later. So they're complicated materials which can be tuned in lots of ways. But beware devitrification. Devitrification means the loss of glassy nature. What it really means is crystallization. If you do something that causes your glass to crystallize, you've lost it. You've lost its glassy properties. So beware devitrification. Okay, a piece we brought back from Pennsylvania somewhere, which I rather like the inside of. Phase diagrams. Now, let me just have a look at your faces to see how many of you are totally bemused by phase diagrams. As a material scientist, of course, I grew up with phase diagrams. They were my everyday tool. I see Steve is grinning, and Barry too. But they're not everyone's taste, and lots of other scientists and engineers don't know anything about them. So let me explain just very briefly what I'm showing here. I'm showing a two-dimensional plot where temperature is on the vertical axis and the composition is on the horizontal axis. And on the right-hand side at 100, it's all silica. And on the left-hand side at 0, it's all sodium oxide there. And if we mix these two, then we've got what I would call a eutectic diagram here. The word eutectic doesn't matter much, but the key thing is the one thing I said earlier. That's the melting point of silica right up at the top here. The melting point of soda is down 900,000-ish, but the melting point of some of their compounds is even lower. So this whole field in the middle is where it's liquid. So instead of having solid glass up here, if I add some percentage of soda, I get lower melting points. And in these fields, these triangular fields here, notice it says quartz and liquid. So it's a mixture there. And then below that horizontal line, everything's solid. And that's as low as 500. 500 is very, very different temperature from 2000 in terms of the energy cost of providing it and the ease of getting a furnace at that temperature. So that's quite important. But as I said, glasses contain at least 3 oxides and usually 4 or 5. So we need the equivalent diagram for 3 or 4 constituents. And again, I spent years studying this, and I still find it awfully difficult. So here is an example of a ternary diagram. So this is the way you would represent the mixture of 3 things, just like in the base glass I told you, just here labeled A, B, and C. But typically, the melting point in the middle here is lower than any of the 3 constituents. That's the important point. So and here's a pretty colored version of a similar thing, showing that you can take a section here. But don't worry about understanding that. If you are a material scientist, you will have seen these before. If, like me, you're not a very good material scientist, you won't understand exactly what you're looking at, but you will know that you've seen it before. I've been a material scientist for 60 years, and I still have great difficulty using these things, so I'm not going to dwell on them. But I just want to point out in this colored one on the right, look at how many phase fields there are. Look at how many different combinations of material with different melting points there are when we just mix 3 things, right? You imagine mixing 5 things, it gets very, very, very difficult to present it visually, but the complexity of what you've got on offer is huge. In fact, I've got a friend, Brian Cantor, who's just finished as a Vice-Chancellor of Bradford University, actually, and has gone back to being a materials scientist. He has discovered phases in the middle as recently as 5 years ago that none of us knew exist, simply because there's so much in there to discover. So that is the complexity. I'm now going to leave complexity behind, I hope, and get on to more generic things. And it's time for a joke or two. A talk isn't a talk if I don't keep you awake with a joke or two. So you'll have all heard the engineer joke, this one. The optimist says the glass is half full, the pessimist says the glass is half empty, and the engineer says the glass is over-designed by a factor of 2. And of course, I count myself as an engineer now because you earn more money as an engineer than you do as a scientist, so it seemed like a good career move. But I quite like, when I was sort of looking for something to go with this, I quite like this one, which I only found a year or two ago. This is physicists in glass. The optimist says the glass is half full, the pessimist says the glass is half empty, and the neutrino says, what glass? Which, if you're a physicist, I suppose is quite funny. I thought it was moderately funny. Right, so back to the course material. This is an absolutely key issue. I just said glasses are amorphous. That was my definition of a glass. They are amorphous, which means they are not crystalline. And I said, in a slide or two later, beware devitrification, because if glasses crystallize, you lose most of the things that you want out of them. So it's important that we understand a bit about crystals and crystallization. So I suggested to Barry and Steve that they might want to use this as the advertising slide for my talk, but they politely declined on the grounds that it needs explaining. This, of course, is an apple crystal. It's an apple crystal in the sense that if I know the position of one apple and I know the size, average size of apples, I know the position of every other apple. All right? So replace atom for apple and you have a crystal. So a crystal is something where the position of each of its atoms is entirely predictable and regular. Right? So apples packed that way do it nicely. However, why don't glasses then crystallize? Why don't their atoms line up in those ways? Well, there's a bit of slump glass, which I'll come back to later. This is one of the reasons glasses are made of more than one thing, and they ain't all the same shape. So if you try and crystallize a box of apples and pears, you have a lot of trouble. I'm not saying you can't do it. You could carefully take all the pears out and hope that there was the ratio of apples to pears was some easy number, and you could line them up in clever ways. But by shaking the box, you ain't going to get a crystal of apples and pears. And that's a bit like our glass. It's made up of constituents which have different properties and different shapes, and it's very difficult to line them up. Not necessarily impossible, but very difficult. So that's one reason why glasses are glasses and they don't crystallize. So if we're doing simple undergraduate two-dimensional sketches of these things, we say quartz is like the picture on the left, where all the atoms are bonded to the same right number of other atoms, and they're in a regular pattern. That's a crystal. But a glass has the same sorts of atoms in, but they're connected in a more random, networky way, and they don't crystallize. And unless you break a lot of the bonds over here, it's hard to get from the right to the left, unless you break all the bonds and remake them in some other way. And it's particularly difficult when all the hollow dots here, the hollow atoms and the solid atoms aren't all the same, right? Which is, we know to be the case in glass. So crystallization is quite difficult. And I'm reasonably familiar with thinking of the bond directions from one atom to four others here, forming a tetrahedron. So the base unit of most glasses is a silicon tetrahedron like that, where the silicon, which is 4-valent, connects to 4 other oxygen atoms. But the oxygen is only 2-valent, so it's only got one spare bond sticking out. So that's why you just don't, but you can stack these tetrahedra. So people thinking about this would think in terms of tetrahedra like that. And they draw diagrams like this. where I've pointed to silicon, the white one there, connected to 4 oxygens, and each oxygen connected to 2 silicons. Right, so that's, if you do that regularly, you get a crystal. If you do it just at random, you get a glass. This is rather nice because I thought it was a very nice piece and it was very cheap. This guy, Ben & Spencer, who operates out of Ireland, sold me that for 40 quid, which I thought was a bargain. So it got me a cheap birthday present for my wife. So to summarize why glasses don't crystallize, 2 things. Start with the second one. I've just said it's difficult when the molecules or atoms are of different sizes and shapes. And also, it's difficult if there isn't enough time. And I'll come back to that point. If something is to crystallize, its atoms or molecules have got to get themselves into the right position to form this regular array. That means they've got to move from liquid phase to solid. And if we don't give them enough time, even if they'd like to, they can't get to the right position. So two reasons why glasses don't crystallize. We don't give them enough time, and it's difficult with atoms or molecules of different sizes. I just wanted a little bit of a diversion now. This is one of my wife's pieces. She doesn't claim to be an expert, but she went on a course or two, and that was one of her flat pieces that she made with slump glass. So I'm going to put you lot over to the right. Here, anyone heard of Prince Rupert's drops? Of the 4 of you I can see, one of you has. I'm just going to show you a picture of droplets of glass. If you melt glass and then draw it out like this and let it form a blob, you get a long thin tail and a pseudo-spherical blob, not spherical. And these were discovered quite a long time ago, but they're actually rather resistant to banging unless you snap the tail off. And if you snap the tail off, you release all the stress, and this happens. Watch carefully. Bang, tail snaps off, explodes. So those are Prince Rupert's drops, which were used as a sort of drawing room amusement 100, 200 years ago, but actually tell us something about the build-up of stress and the fact that once we break that little bit, which is quite easily, we release the stress, and the result that you saw happens. So those are Prince Rupert's drops. And I put them up both as entertainment, but also seriously, because I'm going to talk about how you toughen glass in a minute. So back to my Peter Layton piece, which I so much love, I put it in twice. And when you hear me muttering to myself, it's because I'm trying to move my pictures of you around. Okay, so if we wanted to toughen glass, and we do, then we've got a couple of options, or several options, but here are 2 of the commonest. So annealed glass, like you might have in your windows, and is the cheapest option, breaks easily, and it produces long, sharp splinters. Very good for injuring people who burgle your house, but not very good for safety purposes. So the 2 options which we most commonly find are tempered glass, which does shatter completely when you hit it with a hammer, but breaks into small, approximately cubic pieces, which don't have terribly sharp edges. So although it doesn't necessarily protect you from being broken, it gives a safer product. And then finally, laminated glass, which, as the name implies, is bits of glass in layers with a bit of plastic in between, essentially, so that when you break it, the bits of glass stay where they were and do you less damage. So those are the possibilities. This is the lovely one. I'm showing it the wrong way around, but because I'm viewing and you're viewing in landscape, it really needs to be portrait because that's hung on the wall, and it's a rather lovely piece of glass by a guy called Lavender. So let's talk a little bit about how we toughen up glass. If you know this is obvious. If you don't, it's actually quite difficult to get your head around. The when you suddenly cool, rapidly cool a piece of glass, the outside, blue here, freezes first. And as most things do, it contracts on freezing. Once it's done that, and in the early stages, the bit in the middle is still liquid. And the bit in the middle has then got to solidify, and in doing so, it wants to make itself smaller. So it pulls on the blue bit to compress it. All right, so you freeze the outside. The inside, while it's still liquid, then starts to cool. As it solidifies, it reduces its size, changes its volume downwards, thus putting the blue bits into compressive stress. Now, the significance of that is, if I were to scratch the blue bit, the stress within it is pushing the crack shut. All right, so that is the behavior which inhibits it then failing. So toughened glass is glass where the outside layer, the surface bit, is in compression. I didn't actually mean to change slides there. So that's what tempered or toughened glass is, and it's pretty easy to do. You just have to spray it with air or liquid as it's coming out of your hot system, and this happens. So toughening is relatively easy in engineering terms. Lamination is quite different. You use two bits of glass which don't have to be toughened, but you put typically a vinyl interlayer, something that's going to be transparent and doesn't affect the optical absorption very much, and you glue it between the two bits of laminated glass. So it's quite easy to understand what's happening there. And as I said, failure is all about the surface cracks. Once glass gets surface cracks and you pull it, then it's going to fail. So those are your options for windscreens. Most of our windscreens are the right-hand one now. They used to be the middle one. That's how we do it. Now, I wanted to go on to something I regard as clever engineering. This is a piece, there's a funny story to this piece. It's a piece of Retticello by a guy in Seattle. And my wife and I were on holiday in Seattle, and we went to a glassworks and we saw this piece, and my wife loved it. So I said nothing at the time. When we came home, I contacted this guy on the web, and I bought this bottle. I'll tell you why in a minute. But it was reasonably expensive, and it was a birthday present. So I arranged for it to be delivered to a neighbour. But I had forgotten that there would be import duty payable. So when the postman knocked on my neighbour's door, he was asked for about £100, which, unsurprisingly, he was not particularly keen to part with. So he gave it back to the postman, and then another neighbour helpfully intervened and said, "Oh no, the Goodhews are at number 8. You need to deliver it down there." So it actually got delivered while I was out, my wife was in, and £100 was due, which was the opposite of the surprise that I had been intending. Nevertheless, what is special about this? The special word is Retticello, which is an Italian word. If you look closely, you'll see that the glass has been made, the vase has been made, and clearly it's got those black strips, which were originally layers of rods of black glass fused in, and one bowl has been twisted one way, and a second bowl has been blown inside it, twisted the other way. So the black stripes go one way on the inside and the other way on the outside, but then the bowls have been blown together so cleverly that there is a bubble of air trapped in every diamond. Right, so here and here and here, I've just indicated 3 of them with arrows. In the middle of every diamond is trapped a bubble of air. I am still in awe of the skill required to blow one vase inside another such that it traps air like that. It traps air because the black lines, as I say, originally are rods of glass, so they are proud. They're still sticking up. They're a bit thicker than the transparent glass in between that's holding them. So when the 4 high bits of the diamond hit, there is something trapped in between. But the precision with which you get roughly the same size bubble. They're not quite the same size. That one's a bit smaller than this one. But my goodness, the fact that you've got a bubble in every one, I think is bloody brilliant. So for me, this was a wonderful bit of engineering. To my wife, it was a wonderful visual piece of art. And I think it's a testament to the skill of glassblowers, of whom more in a minute. So that's one bit of skilled engineering, in my view. I just want to say a word about why crystal glass is an oxymoron. An oxymoron, a contradiction in terms. Here's a stuff called crystal glass. And it's an oxymoron because it's not crystalline. From what I said earlier, it cannot be crystalline, otherwise you wouldn't be able to see through it. So it's not crystalline, so why do we call it crystal glass? Well, I call it crystal glass simply because the glass makers have chosen to engrave things on it that make it look like crystal, and they can polish it into the surface shapes which make it look crystalline, but it isn't. That is actually a load of these things, which is I'm far too polite to mention. But the glass itself is full of lead. Originally was full of lead. It's thus very dense, and it weighs a lot. The glasses feel heavy, so you feel you're picking up something special, and it's got engraving and etching on the surface, so you think that it's a crystal, but it's not. It's just ordinary glass, and one of the oxides in it is lead, or nowadays barium, equally dense but less toxic. So that's why crystal glass is, I'm afraid, an oxymoron. It's amorphous. If it was really polycrystalline, you wouldn't be able to see through it, which would certainly defeat your ability, your willingness to part with loads of money for something called crystal glass. So, which leads us neatly to the point, why can we see through glass? And again, physicists will know this, others may not, and I'm going to give a very, very Mickey Mouse interpretation here, only being a part physicist myself. It's all about the band gap. And the band gap is the energy difference between the valence band in the solid and the conduction band. And the conduction band is what makes metals conduct, and the valence band is beneath it. And if the valence band is full, electrons can't move. And that's typically the case in stuff we call glass. So in an insulator, which glasses usually are, the valence band is full, the conduction band is empty, and the gap between them in energy terms is several electron volts. And again, no matter if you're not familiar with speaking in electron volts, because I'll give you a comparator in a second, but that's the key point. Electrons cannot move in an insulator unless you give them enough energy to cross that band gap. So there are no electrons able to move in a glass. Now, photons in the visible range, if we regard them as particles, which for this talk it's handy to do so, carry 2 or 3 electron volts. In silica, like quartz, the band gap is about 9 electron volts. So there is no way a 2 eV photon can give 9 electron volts to an electron to enable it to cross the band gap. So photons cannot interact with the electrons in this insulator. If they cannot interact, they just keep on going and they come out the other side, and we call that transparent. So that is basically why we can see through glass. And you can see why we don't want it to crystallize, because it would change these band gaps hugely, and suddenly there would be ways of scattering photons, and so we wouldn't be able to see through it. So that's very, very simplistic. Photons cannot excite electrons, so nothing scatters them. No band diagrams, because this is supposed to be an accessible talk. If you want more, I at one point thought I'd never be recommending this, but actually Brian Cox's book that he wrote with Jeff Forshaw is actually rather good, I think, and it's rather good on this point. So if you want a slightly less simplistic explanation of band diagrams, try that. Okay, another thing that you might or might not have heard of is metallic glass, or glassy metal, called by the Americans met glass. You can't spell, so they only put one S on it. And it's a glassy metal. Now, when I was a boy, in other words, when I was doing my PhD in the 1960s, this hadn't been discovered, and I didn't believe it. So when, as the students and postdocs were gathered around the table and this paper came out, we didn't believe it, basically. We thought the guy had got it wrong. But he had managed to produce metal, an alloy composed solely of metallic elements that behaved in every way like a glass. In other words, did not crystallize. And so let's just reinforce or remind you. So here on the left at A is a crystal. All the atoms are in a pattern that we can predict. In B in the middle is a polycrystal, crystals which are relatively small and not quite parallel to each other, but each one is a crystal. And then on the right, an amorphous material like a liquid or a glass, where knowing the position of one of those atoms, you can't predict accurately the position of any of the others. So that's the spectrum of things on offer. And what these guys did, which I now know to be true, which I didn't believe as a student, is called melt spinning. They melted a very complicated alloy. Here back to my starting point. Glasses have lots of constituents because you don't want them to be made of all the same size atoms. So these guys mixed together lots of metallic species, but they were all different. And then they sprayed it onto a fast rotating copper wheel, which cooled it very rapidly. So back to my reasons for there being a glass, you don't give it enough time. So they gave it literally less than a millisecond to rearrange, and they made it very complicated. And here's how they did it. This was the sort of setup. Here's a copper coated wheel which would rotate. Here's a induction furnace melting your constituents, and here's a gas line blowing it out onto your melt spinning wheel. That works, and it produces metallic glass, and it's for real. And it's used for tape recording heads because it's very good with magnetic flux. It's used for transformer cores. It's very corrosion resistant and surprisingly tough. In other words, it resists cracks. And it's also sold to you as golf club heads, especially putters, like this. I've got a demonstration that I got from a golf pro, but I don't dare show it on Zoom because I tried once and it went wrong. So I'm not going to try a demonstration. But the elastic properties of this metallic glass, matte glass, are very different from ordinary crystalline metals, and they bounce a lot more. They return a lot more energy that you put into them when you bounce them. And so putters, the face of a putter here is often made of metallic glass. So I realise I'm perhaps sort of stop in 5 or so minutes. So I'm going to I think I'm all right to show you a couple more things. I mentioned float glass. Actually, I'll just put some faces up so I can see if Barry or Steve are grimacing at me. Now I'm getting the thumbs up. Okay, I'll go on for at least a little while. So let's say a little bit about float glass, because wonderful British invention, and it reveals quite a lot of interesting things. I said earlier that this is a very, very schematic float glass plant. At the left-hand side here in the red end, you mix together a whole load of glassy stuff. And from what I said earlier, even when you've mixed in the things that are going to reduce the melting point of the quartz, you're still going to have a quite high temperature and you want it to flow easily. So this might be 1600 centigrade, an expensive thing to produce. You then let it ripple out of there and you float it on molten tin. So this is the float bit of float glass. Not quite sure how they came up with this idea, because tin actually has quite a low melting point. It means it's easy to melt, but it's a lot lower temperature than the glass on top of it. So it floats on this bath, which has the wonderful advantage of making it very flat. And in that float bath, it lowers its temperature from about 1100 when it comes in to around 600-ish when it comes out. And it then goes into an annealing layer. And this word layer just means furnace, I'm afraid, or oven. And it's only used by the glass industry, as far as I can understand. So glass technologists call a furnace or an oven a layer for reasons I've no idea about. And then it comes out of there, so it's annealed at 600 downwards, and then it comes out and is chopped and inspected and so on. Interesting thing is that the melting point of tin is only 232 centigrade. So you're floating stuff that starts off over 1,000 on tin that is at 232. So it's just as well you cover it, because otherwise you'd have a lot of tin vapor around, which I'm sure is not very healthy for you. But it's all covered with the glass as long as the process is continuous. So that's quite interesting, and it gave glass of a quality and smoothness that could be used pretty well straight off the line, and that was the key point. So that's float glass window, which you might use for windows. That is not the view from where I'm sitting at the moment, I regret to say, and it's used. Let's just say a little bit before we get on to high tech. I mentioned earlier slump glass, and now you'll realise that slump glass, which is putting a flat bit of glass onto a former and heating it up so it slumps into the shape you want. Very, very simple technique, beloved of glass makers, because in principle it's so easy, as long as you get the glass right and the temperature right. And that will be slumped at around 700 centigrade. A more reasonable temperature to get in your glass artist's workshop, and you can see the effect of slumping. And it also is just enough to fuse. So that bit of Connemara blue that I showed you earlier and is here small again, lots of bits of different coloured glass put on top of each other in the hope, and in this case reality, that they would fuse together. Now, clearly temperature control is quite key here, because if you get it too hot, it's going to run. And if you get it too cold, it's not going to slump or fuse. But if you get it right, you get these nice effects. And that Sally Dunnock big dish I showed right at the beginning is the same technique. So that's slump glass. Oh, I've covered over my own label there. What did I say? Yes, and it's fusing the glass together. The other obvious technique that you know about is glass blowing. And so I've got a picture here of your archetypal glass blower. Glass blowers have to be bearded. They have to wear a blue t-shirt with sweaty armpits and bare forearms, and they have to be quite strong both in hand and lung, because they're going to blow down that tube. So this is glass blowing. Many of you may have seen it. It's fascinating to watch and very skilled. And here is a bit of that reticello, a reticello bowl being annealed or in a flame there, and here it is in the glory hole, as they call it, being warmed up again, because the glass artist works on the bit of glass until it cools down a bit, and then it gets too stiff to work, puts it back in the glory hole here, warms it up, takes it out, does the next thing. So it's a constant iterative process, and that glory hole will be somewhere in these temperatures, 800 to 1100, depending on what the glass is and what he or she wants to do with it. And I'm in awe of their lungs too, because they blow through that hollow tube while twirling it all around and carrying something quite heavy to produce the artwork. So that's glass blowing. I thought I'd end with a bit of higher tech. So the other thing that we are using today, as I said earlier, is optical fibre and transmission. So a little bit about glass fibres. Basically, at the top of this diagram, it says quarry products. So anything you put in there, recycled glass, your quartz, whatever you've got, melted in the furnace, high temperature, as I said, push it out through nozzles. And the nozzles are made of platinum rhodium. It's quite an expensive bit of the kit, this. Platinum rhodium, because it doesn't dissolve in glass and it doesn't stick to it. It's all to do with the surface energy and so on. So the nozzles are platinum rhodium alloy. And then glass fibres are often sized. You don't realise that, but actually a size is sprayed on them to make them more handleable and a bit thicker. So there's often a size, especially when you're going to use it cheaply for insulation or GRP car components or something. And it's then going to be chopped for some applications, or wound onto a drum. And the other thing I wanted to mention is that there are lots of different glass specifications. If you get ordinary glass fibers, they're usually E-glass, and I won't say any more about that, but you can look up these various compositions, A, E, D, R, and S. And of course, nowadays, this is rather important because we use glasses for their thermal properties to keep the right rays in and the right rays out in our windows and so on. So, glass composition is quite sophisticated nowadays. And the diameter at the end here, when you're rolling it up, it's going to be somewhere between 3 and 20 meters, sorry, micrometers, where human hair is a bit under 10 micrometers. So from thinner than a human hair, of which I don't have many to boast, and 20 meters, which would be probably a fiber covered in size, and that's the diameter of the whole thing. So that's your glass fibers. Interestingly, it's got a longer history than you think. The first glass fibers were actually wound into a dress in 1893. I find that astonishing. It must have been a bloody uncomfortable dress, I reckon, because fibers would have been relatively thick in those days and not easy to weave, but you could do it. And then fiberglass, Owens Corning made their so-called fiberglass with the fiber spelt wrongly in the 1930s. And it wasn't until the 60s, as I said earlier, in the UK that we turned them into optical fibers. So they've got a long history, glass fibers. And what happened there? Something happened there. I'm not getting change of slide. Sorry, folks. For some reason, my screen has frozen. Can you hear me?
I can hear you. Yeah.
You can hear me? Right.
Yes, loud and clear.
For some reason, my screen has frozen and even Escape won't get rid of it.
Is this your last slide or?
No, well, not last, but one or two.
Okay.
Let me just.
It's funny because your image is fine.
Right, I'm just going to open it again.
Yeah.
And see if I can get it back. There's only a couple more slides. So that where is it? Right, I'll just. Oh, I think it's crashed out completely. PowerPoint has crashed.
Yeah.
Here it comes. Here it comes. You can see that? Can you? That it's coming up.
Yeah.
Yeah. Okay.
Yeah.
I'll just open it again. And, it wouldn't be a talk if something didn't go wrong, would it? I always used to say when I was a boy. Right.
It proves it's live.
I can rapidly get to the end, I'm sure. Right, there we go. That was my bouncing balls demo. All right, well, I didn't do. Here we go, float. Right, we're nearly there. Windows, slump, glass blowing. We're back. Okay, so just finished with optical fibers. You'll all recognise the fibre broadband is here at the end of your street. And just to say a little bit, the fibre here has to be pretty good, but it's quite interesting to see the scale of the thing. On the right here, the jacket makes the fibre that the guy handles in the hole in the road about 1 millimetre diameter. 900 microns is 1 millimetre, but it's got a buffer, it's got cladding, and the actual core fibre is about 8 microns in the middle there, inside which you've got a central core down which the light actually goes. And I won't dwell on this, it's too much physics, but there's lots of different types of index. I said you could tune the refractive index of glass. Well, this is where it comes into its own, and you can make the light going down your glass fibre do different things. Step index here, graded index, single mode, so it only transmit one wavelength and so on. So all those things can be designed in by the diameter and the refractive index of the glass. I would, that was a question that I set for students, and you can answer if you like, but I'm going to skip past. So to recap, we touched on what defines a glass, a little bit of history, 5,000 years, bit of composition and phase diagrams, why glasses don't crystallize, why they're transparent, a few applications, and we had a background of art glass. Did you notice, you should do because I was trying to emphasize these things, did you notice high temperatures, so high energy costs, one big snag of almost any glass, lots of elements, so complex chemistry and material science because there's a mixture of a lot of things, and I gave you no maths, which I could have done, but I chose not to for this and most other audiences. And of course, finally, what a beautiful subject to be working in. As you'll gather, I'm quite enthusiastic. Might be my wife's passion, but I largely share it. And so thank you very much for listening to me. Finally, glass, china and reputation are easily cracked and never well mended. So I hope I haven't cracked my reputation today. And here is a sampler of what you've seen. Thank you very much.
Oh, brilliant. Thanks so much, Peter. That was great. And anyone who says that the worlds of art and science can't mix, I'm afraid that's been disproved by your presentation, because I think the combination of the science and the visual art, the glass there has been really great. So appreciate that. Gonna make some time now for some questions and answers. There are a few comments in the chat box.
I wasn't looking at that, so I missed that.
Sorry?
I said I wasn't looking at the chat box, so I'll...
No. Well, I'm going to go through it now. There were a few questions came in, so I'll just go through them briefly. One of our correspondents, Carol, is reacting to your thing about engineers earning more than scientists. She's pointed out that for a reason that's not always the case. Depends who you work with. I
agree. It's not always the case. I was joking.
Okay. So there's a question here from Mike Hollingsworth. Nice to see you again, Mike. He asks, how does adding soda and other substances actually lower the melting point of silica?
Well, behind the answer to be genuine would need to be quite complicated, I'm afraid, so I won't give a full answer. But behind the phase diagram lie what are called free energy curves. And if you look up free energy curves, you'll find that the free energy of a mixture of things changes as you change the composition of the mixture. And the free energy arises from the energy of the bonds in between the various materials you're making and the entropy. So the answer has a lot to do with entropy. Pure quartz has lower entropy, right, than a mixture of silica and soda, because you've got more species present, more possible combinations, so the entropy goes up, so the energy goes down. If I could just say G equals H minus TS is the answer to your question. For those of you who know what the Gibbs free energy is and S is entropy, that's a full answer. Those who don't, skip over it.
Thank you.
Well, I'm sure the physicists here understood that. I'm afraid as a biologist, I'm completely
I recognise
above my
even entropy isn't widely understood.
Okay, moving on. Here's a question I think we can all understand. Oh, it's from another Barry. Hello, Barry in Bramall. He asks, that's a good question, as tin, this is talking about the float glass technique, as tin is only in contact with one side of the glass, why is the glass flat on both sides?
That's an excellent question. Actually, I hadn't thought about that before, but I think I know the answer now you pose it to me. I think the answer is that surfaces which are able to move, fluid surfaces, like to be flat. And the reason is that's the lowest surface energy configuration. So they're trying to minimize their energy. A flat surface has lower energy than a wavy surface because it has lower surface area. So in the absence of disturbance, things like to be flat. And the tin bath, it's very convenient for moving the glass over because it's much finer scale than rollers, which might be the other alternative. So it's supporting the glass, but it's flat principally, and this applies to both sides, because it wants to lower its surface energy. And what you mustn't do, of course, is kick the furnace while it's going through, because ripples would pass through the glass as they would pass through water. So that's the fundamental answer. It's a surface energy issue. Surfaces want to be flat. As a flat mill pond within the absence of wind would be jolly flat.
Yep, that answer works for me. Okay, I think that's all the questions that are in the chat box. So I see we've got a few hands raised. So we'll start with Peter Weston. If you can unmute yourself and ask your question.
He's talking without unmuting himself.
Peter, can you unmute?
Oh, he's killed the video. It's the other button.
Oops.
Okay, is it better? Can you hear me?
Yes, thank you, Peter. We can hear you.
First of all, Peter, I am in awe of this presentation. Absolutely brilliant. I can't think of really, really lovely and full. I've got a couple of questions. One question is really about the ability of glass to transmit infrared. What the kind of factors can be achieved, and is there any inherent reason why the cost of producing glass, which has this property for windows, is more expensive? It seems to be a lot more expensive to buy this type of glass compared with the normal manufacturing process, please.
The first part of your question is quite difficult as the whys and wherefores is quite difficult, and I'm not, I have to say, a glass scientist. I only know what I know by having picked it up over 55 years. But the other question as to why it's more expensive, I think anything you do which is not bog standard is going to be more expensive. And I think most of the things that are sophisticated that we can put in our windows are not uniform. So they have different compositions, one side and the other, different surfaces which reflect more or less and different wavelengths. So they are more complicated to make because they have different layers. That's the answer to why they're more expensive. Don't ask me to unpack that in more detail because I don't know any more detail.
Okay, thanks very much indeed. Thank you.
Okay, thanks, Peter. Next is Ronnie James in Wolverhampton. Ronnie, can you unmute? Thank you.
Thank you very much. One never realizes how much there is in something so simple as glass, but thank you for a lovely explanation and talk. Can you say something about self-cleansing glass? How is it made and how is it different?
It's got a surface layer which has been engineered to have different surface energy properties. It's self-cleansing in terms of its the energy between water, which is the principal thing, and the glass. And by changing the composition of the glass, you can make that interfacial energy different, which changes the behavior of the glass from balling up into droplets or spreading out, wetting. You're familiar with the word wetting, right? And things wet, liquids wet glass when the surface energy they create is being wiped out by them being covered by water rather than glass. And by tuning the composition of the surface, you change the surface energy between the liquid and the solid. And that means glass is wet. Now you do it superficially, of course, every time you put wax on a car. The surface energy between the wax and the water, which repel each other, is such that the glass forms droplets and runs off. Unfortunately, your wax wears off as well. So what they're doing to the surface of the glass is it doesn't look like wax, it's just a change in the oxide composition, but it has the effect of changing the energy of the interface between glass and the dominant liquid, which would be water. Does that make any sense?
Sounds good to me.
Well, Yes, is it something to do with the surface tension of the water as it falls?
Yeah. When I say surface energy, yes, surface tension is the common term. We tend to say surface tension when we're talking about a liquid in isolation. So a droplet forms a sphere because the surface tension pulls it into the lowest volume shape, lowest area shape, which is a sphere. When I say interfacial energy between a glass and liquid, that's simply the surface tension of that boundary, really. So I'm using surface tension, surface energy almost interchangeably. Technically, they're not. One's an energy and the other's a force, but they're effectively the same concept.
But that is the result of some sort of special surface on the glass.
Oh yes, yeah. It's a different. They've changed the composition. I mean, there's lots of ways you could do it. You could irradiate. You could implant a different material into the surface of the glass. That'd be very expensive. So it's not likely to be used for architectural glass. But there's lots of things you can do to change the surface. As I said, lots of oxides dissolve in glass, and if you just put a little bit down, it only dissolves in the first, 5 microns. Then you haven't used much material, but you've changed the properties of the outer layer.
Thank you. Thank you.
Thanks, Ronnie. Chris Smith in North Devon.
Hi, Peter. Thanks very much for a really wonderful, excellent talk. I'm a big fan of glass, and I've been to Murano myself, got quite a few bits. You mentioned it just in passing, glass transition points.
Yeah.
I'm an ex-paint man, industrial surface coatings with quite elaborate methods of applying them, and it was always very important to us when we apply particular types of paint, particularly powder coatings, that they achieve their glass transition point at a certain stage before you commence the cross-linking and the initial filming, formation of the final film. And I think probably what you've explained is probably used in a different context, or am I talking about the same thing? The glass transition point was always very important prior to the final heat for cross-linking.
No, we are talking about the same thing. I skipped a couple of slides, which I'm not going to go back to, but I'll just say a few words. The glass transition is where measurable properties change from being glassy to being more elastic or more like a polymer. So it changes almost like and so externally you might not see any difference, but in terms of the behavior of the material when you stress it, it makes a big difference, which is why you would have been worried about it.
Yes.
Inside, in terms of what's going on inside, you can imagine there'll become a temperature at which bonds can rotate. So atoms can move. If you imagine all the bonds between the atoms or what hold it together, there'll come a temperature where the molecules can rotate, so bonds can rotate. There'll come another temperature where you break some, and that's a higher temperature.
Yeah.
Right? And when you start breaking some bonds, then you can do one set of things. You can melt it. When you start being able to rotate them, then you can manipulate the glass before it gets melted. And that's your sort of glass temperature. Very, very, very crudely.
Yeah. Yeah, it was very important with certain of the more higher technology powder coatings we use in the automotive and space age applications.
I should have issued a caveat at the beginning. My experience of a U3A audience is that there is always someone in the audience who knows better than I do about anything I say. So
not in this case. I thank you because you've explained a concept I used. I didn't really quite fully understand it, so thank you.
A very glib and superficial explanation, I'm afraid.
Thank you.
Peter.
Yep.
Peter, I have a question. Can we go back to your glass fibre piece, or rather fibre optic? Did you explain why, although glass is very, very brittle, why fibre optics, I know they're very, very small, 8 microns, why they don't snap when you bend them?
Yeah. I set that as a one for the students. It's all to do with the radius around which you bend it.
Yes.
Because if you've got a thick piece of glass,
yeah,
a thick glass rod, and you bend it round a former, it will, of course, you'll put the outside in tension, you'll put the inside in compression, the outside, any cracks, it'll break.
yeah,
But if you do the sums for a thickness of only 10 micrometers, you would need to bend it round a former that was smaller than a millimeter
really?
before you got sufficient strain in the outside for it to crack. So
Remarkable.
it's just a scale thing. It will crack in it just the same way as a bigger bit, but you'll have to wind it around a smaller hole. Now, so winding it around your finger isn't enough.
Right.
That scarcely stresses or strains, it scarcely strains the outside of the fibre, winding it around your finger. So that your guy down the hole can do what he likes with it.
The strain on the sheathing is probably a lot more than actually in.
Yeah, absolutely. It'll be worse for the outer.
That's a limiting factor.
If he were to see, he'd see the sheath cracking before anything happened to the fibre.
Yeah. One other point I had. It's been said, and I guess it must be true, that glass remains a liquid. And you can see this when you visit a National Trust property and you look at some of the old windows. You can see that the glass has effectively drooped over several hundred years of aging, and it's thicker at the bottom than it is at the top. Now, is that something that we would expect our modern day glass to do in 200 or 300 years? Will my double glazing look like these National Trust properties, or is it that the additives that we have nowadays, the material science, makes the glass that much harder, and it will take longer for it to droop in the way that older glasses do?
I mean, like you, I've heard all the anecdotes, and it's what you've just described is commonly said. I'm not sure whether or not it's true. I think there might be other explanations for the glass not being of uniform thickness, like the imperfections in their manufacturing.
Yes.
However, technically, it is a sort of frozen liquid. Back to what I was saying about the glass transition point. If you heated it above the glass transition point, then it would very gradually change its shape. But whether the glass transition point of the window glass available 300 years ago is right, I just don't know.
No.
But so I'm afraid I'm going to give a on the one hand and on the other hand answer because I just don't know, and I've never done the sums.
No, it's interesting. And coming back to your comments about bending glass, I'm always in awe of what you see, particularly in the car manufacturing industry. The shapes that these windscreens and various other bits of glassware on cars are made to form. Is it really an expensive process to do that?
Once you've calculated the shape,
yeah,
it's quite easy to slump a piece of glass into that shape, right?
That's all it is. It's just stamping, is it?
Yeah. I mean, when I say slump, that's what a glass artist would do. They put it in the furnace and walk away for overnight. But in the windscreen case, they've got a press, right? But the key thing is the shape of the mold into which they're pressing it. And it's the calculation of that gives you the complicated shape. Pressing it to that shape is the work of probably 2 seconds in the automated press.
Yeah.
So that's pretty easy.
Can it be done in very low volumes? What I'm getting at is, say I had a vintage car and I needed a new windscreen for a Morris 1000 or something even older that had a curved shape, not too difficult. Could that be done on a sort of custom basis economically?
I think the answer to any question of that nature about it is custom tooling. A custom tooling is very expensive. If you think of that, you've got to make a tool which is the size of your windscreen, which is going to be, 1.5 meters, 2 meters long and half a meter deep. And you've got to make that the exact shape you want the windscreen.
Yeah.
And then heating the glass and lying it on it is a trivial problem compared to the time and and cost. You've got calculating and then making that mold. It's making the tool that is the difficult.
I understand. So there's probably a very good market then for the old tooling that comes out of old British factories and so on. People collect that tooling for future use, and it's very valuable to them for future business.
I imagine, but I don't know, that there will be similar molds for, shall we say, I used to have an MGTC, for the mudguards of my MGTC, which are a quite complicated sheet form. That's easiest made if you've got a mold that's that shape out of wood and you hammer it round it. Those things probably exist still.
Yeah.
Steve, there's another question appeared in the chat box, which I'll read out in a minute, but I just wanted to come back on your question about this business of old glass and gravity causing it to slump. And I'd heard that as well, but I'd also heard the explanation that, in fact, it's not that at all. It's the fact that plate glass used to be made by getting a big blob of glass and basically spinning it very fast, and it sort of expanded outwards into a sheet, and then they cut it in the plates for the windows, and that's why the windows are not necessarily optically uniform.
Yeah,
I think that's correct, Barry. I've seen that too, and I'm sure that's right. But if that was true, you wouldn't always expect to see the thick bit at the bottom, unless the guys felt that that's the way it fell when you held it, the heavy bit at the bottom.
Right.
Yeah.
Who knows?
It's fascinating. Yeah.
Anyway, look, I've just asked this question that's appeared in the chat box from Mary. I must have not heard of uranium glass. She's asking about uranium glass, and she's wondering whether it's possible to actually extract uranium from uranium glass. But don't go giving Putin any ideas, or the Iranians.
That's a new one on me. I've never heard of uranium glass, although because oxides of uranium are very common, that's how we extract the uranium from. I can well believe it's easily possible to make a uranium-containing glass, and it would be presumably denser than barium or lead glass.
Hello, Peter. Can I chip in here? Sorry you can't see my lovely face. Apparently, they add it as an oxide of diuranate.
Yeah.
And it's added before melting, and it goes from a trace element up to 2%, although in the 20th century they had up to 25% uranium in there. Now it was basically used for entertainment, because if you shine UV light on it, it glows. I just wondered how safe it is. They actually banned it from being used in case, because they needed the uranium for military purposes, so they stopped allowing it to go into the glass. But the US Nuclear Regulatory Commission says that it's dangerous to drink from, so you shouldn't drink from glasses that have uranium in them. They say it's negligibly radioactive, but I just wondered what happens with all this uranium glass out there, whether it fell into the wrong hands, people could actually be extracting the uranium from it, using it for military purposes.
Well, as you'll be aware, I mean, it's a radioactive isotope that you need. So I've got an echo. Anyone
Yes,
else?
there is an echo. If anyone who's
Someone's got a feedback loop somewhere.
I'm going to mute you, Mary. There's an echo. How about that? Has that stopped it?
That's better, yeah. If you can still hear me, Mary, apologies for cutting you off. Yeah, I can just about believe the toxicity of drinking from it. I think it would be a pretty expensive way to get radioactive isotopes of uranium, because if they say it's only marginally radioactive, as it would be with natural levels of U3A, or which one, I always forget which is the radioactive one, I don't think we should worry. Uranium is widely used in the military for its density. I mean, armor-piercing rounds are often loaded with uranium just to make them very heavy and dense and pointed, so they'll penetrate armor. And you don't need anything very subtle for that. You just want quite a lot of uranium in a small package.
Thank you for that, Mary. And thank you, Peter. Do we have any other questions? Oh, there's something's popped up from David in the chat box. What makes a glass blower? He's delighted to see talented glass blower Ingrid Piers. Lovely lady, apparently.
Without a beard. Yes, very good question. I mean, there are female glass blowers, and I've seen a small number. The majority seem to be male, but I think it's just something as if you're prepared to give it 10 years and stand in front of a hot glory hole for a goodly number of hours a day and exercise your lungs, then anybody can be a glass blower. But it is quite physically arduous.
Yeah. Yes, I've had the pleasure of visiting Caithness Works, both in Scotland and King's Lynn. I think they have one, and also Murano. I visited there and had a demo, and it's absolutely fascinating to watch these people. So skillful, and incidentally, in my past career, I visited Mullard, the then Mullard company in Southampton, and of course they had a whole team of expert glassblowers for their vacuum tubes and cathode ray tubes, all the rest of it. And of course, the semiconductor industry largely put paid to that. But in that particular stage of my career, they were still doing some experimental work on infrared detectors. And in order to cool them cheaply, they were put into essentially thermos flasks, custom made by glass blowers at Mullard's. So yeah, they still have one or two employed, but a dying breed, unfortunately.
Certainly, in most of my career, any chemistry department in a university would have glass blowers. In the old days, and materials departments would have glass blowers to make custom stuff for your research labs or whatever. But that's not quite the same as blowing large chunks of art glass, but still some of the same skills.
Yeah. Okay. Any more questions, anybody? Put your hand up or make yourself known. We've got lots of thanks for you, Peter, in the chat box.
Yep.
So, yeah, absolutely. It's been a fantastic talk and so well illustrated. We've all enjoyed the artwork and very high quality slides, Peter. Really, really nicely done. And I'm sure folks appreciate the lack of mathematics, but the content was very instructive nevertheless. And yeah, absolutely fascinating.
Some people would berate me for the lack of mathematics. I think I'm having an argument with my wife at the moment about whether I dare put anything vaguely mathematical or scientific in my chairman's remarks in our monthly newsletter. I'm told I mustn't mention science, engineering or maths in my monthly newsletter. And I say, no, I must mention it, because one of our problems as a society is that we don't expose our population enough to science and maths. So I'm colluding in this if I hold back from talking about something I know a bit about.
I'm in total agreement with you, Peter. Yeah. As the Science and Technology Group leader for my local U3A and as newsletter editor, I personally see to it that there's some S&T in the newsletter. So yes, indeedy.
Good.
Yeah, that's marvellous. There is a question in the chat box on, I don't think we have time to it, but it's what are the physics of glass cutting methods?
I can answer that in a couple of seconds. I mean,
go ahead.
You use a tool which scratches the glass.
Yep.
That's what I've just told you. If you bend the glass so the scratch is in tension, it'll break along the crack. Easy. Slightly harder to cut circles, but the same principle applies.
Yeah. Okay.
There you are.
Well,
short and sweet.
Yeah. Peter,
like
thank you so much for a brilliant talk. You had us all in awe, and with your permission, I'll pass on the news that you have a talk about the future of engineering education. I think that will be an interesting one for the AI community later on. And now I must nip down to the shop and buy a piece of obsidian. I must get my own piece, as must we all.
I don't have one.
But you rightly said, I think as U3A members, we all need something like that. Well, thanks once again. Please, everybody, show your appreciation for Peter's talk this morning.